The math here on 6C is as much for my entertainment as for your information. But seeing the math allows us to prove and kind of support some concepts that are super important for either a free response, but especially a multiple choice question. So when we have a polyprotic acid, you have multiple values of K, a Ka for the first ionization, the second ionization, and then if there's a third, and can't think of any, but potentially if we got into some big biomolecules, a fourth or fifth ionization. We would be focusing on chemistry molecules that likely have 2 to 3 ionizable hydrogens. Phosphoric acid is a great example, and it's the kind of most common and maybe strongest of the weak polyprotic acids. And with that, we notice that Ka1 is to the negative third power, 2 is to the negative eighth power, and 3 is to the negative fifth power. There's a difference of about 5 powers of 10, or about 10,000 orders of magnitude different. So since the first one's way bigger than the second or the third, the only hydrogen ion that will significantly ionize enough to impact the pH would be that first one. So the first ionization is a normal Ka over equals x squared over the molarity. I've got my table here. I do my estimation. It is right on the border, but it's still good enough that we can do that estimation. Even if we checked our work with the 5% rule, we'd see that the minus x doesn't make a big difference. And we would see I have a certain molarity of hydrogen ion. What's important to note here, conceptually, even though this is the strongest or the biggest ionization of all of them, we only have 0.02 or rounding off 0.03 moles per liter of the two products of that ionization, and it's still 0.97 even if we do our subtraction, or 97% this and only less than 3% of these. So conceptually, the most common ion is for sure the unionized acid, hydrogen ion, and the first anion or the first conjugate base are much lower, but they're still there. Well, this, we called it the first conjugate base, but it's amphoteric. It can act as an acid. So a small amount of that can go away, producing a little bit more hydrogen ion and the HPO4 minus, the monohydrogen phosphate ion. For this, that is the second ionization, so we have to use Ka2. For these, I am going to include my plus and minus X, because if I totally ignored those, I wouldn't be accounting for how much more hydrogen ion there actually is. Mathematically, it wouldn't really make a big difference. And we'll see that is basically this is 0.027, this is about 0.027. If we cancel those two out, we see that X is pretty much equal to this value right there. Or the amount of the hydrogen phosphate ion is very, very small. And we've only made a tiny bit more hydrogen ion, 0.000000006. Barely enough to notice more hydrogen ion. Well, that thing that I made a very tiny amount could further ionize. There's already some hydrogen ion there, though, from the first ionization. So that hydrogen ion, I still have, most of it came from the original phosphoric acid, but a tiny bit more can ionize here. And the most important part here is to realize, well, how little of it actually turns into the total ending base, if we will, or the phosphate ion without any hydrogen ions or protons. So when we do that, we find out that X is equal to this, and our hydrogen ion total concentration is this, plus a tiny decimal, plus a tinier decimal, to give us really just that hydrogen ion concentration from the first one. When we do the negative log of that, that gets us our pH. So more important than the proof from all that math is the idea that we have 90-something% of my unionized original polyprotic acid. we have 5% or less has turned into hydrogen ion and the first conjugate base. And then even less is turning from that into the next. And then we're going down not just a little bit, but in huge orders of magnitude. We're 10 to the 10th or over 10 to the 10th times less. So billions of times less here in terms of those ions. That's when it's ionizing by itself. And what we'll do coming up is compare that to what happens when it is reacting with the base if we had either a mixture of acids or a polyprotic acid that is doing a titration.